For this AP Statistics video, we are looking at lesson 5.3a, which is focusing on conditional probability and its relationship with probability independence. And so when we're focusing on independence, we need to understand what that means. What we're going to do is we're going to focus on the data we collected before with the idea of, are the events taco tongue and evil eyebrow independent? So we looked at a two-way table and a Venn diagram of that data before. So we're going to use some classroom data that we collected from the previous lesson based off of your ability to taco tongue or your ability to evil eyebrow and determine, are they independent of each other? And when you're looking at independence, we want to focus on the definition, and it says two events are independent if the occurrence of one event has no effect on the chance that the other event will happen. And so, of course, what does that even mean? And so we're going to focus on trying to understand that, and the big focus on it is to be very careful to not confuse it with mutually exclusive. Our world definition of independence is not the same as the probability definition of independence. So we want to keep that in mind as we go forward. So to determine if some two things are independent based off probability, we need to perform calculations. So let's just go right into the data from before. So we can see off to the side we have our two-way table of the can you evil eyebrow, can you taco tongue. And so in this case, we have our information and we're going to dive into it answering these two probability questions. And the first one says, given that the person selected is a yes evil eyebrow, now that's interesting, what is probability that they are a yes taco tongue, right as fraction decimal, and a percent. So when we're going through this, I want to focus on this wording of this. Given that, that phrasing right there is extremely important. That means we are focusing solely on given that the person is a yes evil eyebrow. So we are looking really at that section right there. We are focusing on making sure that we are only seeing this. Yes, this had to occur. Given that we are in this column, what's the probability that somebody can yes taco tongue? And in that case, what we have is we have 15 out of the 18. So given that we're focusing solely on individuals in this column, which there's 18 total, what's the probability that they can yes taco tongue? Well, that's 15 out of the 18 total. So I just wrote it as a decimal, 0.833, which would be 83.3%. In symbolic form, what we're dealing with is this notation. Probability of yes taco tongue, you see this vertical line, yes evil eyebrow. You can see I tried to color code it, is the given that right there is what this represents. So given that yes evil eyebrow, what's the probability that they're going to taco tongue? So we're going to get used to that notation in this lesson. So we can see how notation has been building throughout this whole section. So the next part says, given that the person selected is a no evil eyebrow, so you can see right here why I have that column highlighted. We're only focusing on that column. What is the probability that the person is a yes taco tongue? Well, it looks like only 5 out of 12 in that column. So I'm thinking it's 5/12ths, which is about 0.417, which is about 41.7%. Now, let's kind of look up above to try and figure out how that relates to the notation before. So given that the person selected is a no evil eyebrow, so something's telling me here's the given that, this part should be my no evil eyebrow. And it is. Given that there's a no evil eyebrow, what's the probability of that event occurring? And so we see how these relate to each other. Now we have this given that, which focuses either on a specific column or sometimes a specific row, and then we're looking at the intersection. We call that concept conditional probabilities. Something has been put as a condition. Given that, we're only focusing on students who cannot evil eyebrow. So when you put a condition in play, that's when you start using this notation. And so this right here is our given that. And this is really what conditional probabilities is, which is really what half our lesson is over. So let's move on to the next example. So now we're looking at part C, which is saying, based on our previous two answers, which are down there, what conclusion can we make? Well, we can see that if a person can evil eyebrow, yes evil eyebrow, they are more likely to be able to taco tongue. We can see that because this percent right here is larger than half, and this percent right here, 5/12, would be less than half. So given that they have this ability, they will more likely be taco tongue. So if I'm trying to figure out, hey, can someone actually do a taco tongue? So can they do this? Their ability to evil eyebrow has an impact on that, which this kind of leads me to think it's something with independence is going to play a role. And so that's where the next problem comes into play. Again, you can see that we have our data from before right down here, and I have the definition again. We made the conclusion people who can evil eyebrow are more likely to be able to taco tongue than those who cannot evil eyebrow. The definition we looked at before for independent events says two events are independent if knowing whether or not one event has occurred does not change the probability that the other event will occur. And what we did is we built towards this definition of independence. So if we think about this, if I want to know, can somebody taco tongue? So I want to know, can somebody do this? And if they can, I want to know, is it impacted by their ability to evil eyebrow? So we can look at the information and go, okay, if I'm looking for, can they taco tongue? Does their ability to evil eyebrow impact that probability? And the answer is yes, it does. 15/18 is not the same as 5/12. So are these two events independent of each other? Probability independence. And no, because knowing whether or not a person can evil eyebrow does change the probability that they can taco tongue. And I want you to kind of look up above to kind of understand that definition. Knowing whether or not they can do this. If they can evil eyebrow, it does change their probability to be able to taco tongue. That means one impacted the other. So they are not going to be independent of each other. So this is a really hard concept because our definition in our brain of what independence means is not the actual statistical probability definition of independence. And so we're going to have to keep this in mind of we have to calculate probabilities and compare them to see does the probability change. And that's where this definition is really going to start coming into play more. If two events are independent, knowing whether or not one event has occurred, knowing whether or not they can evil eyebrow, should not impact the probability of the other event. And in this case, it did. And so therefore, they were not independent of each other. So let's dive deeper into this probability independence idea. And for example 4, we have used this data. We have 600 seniors at a large high school. All the data is in that two-way table right there. And now we're being asked to find each of these probabilities, write them as a fraction, decimal, and a percent. I wrote them as a fraction and a decimal, and I'll just say the percent out loud. Probability of yes, somebody can taco tongue. That's straightforward probability. We are only looking at that row, and there's 480 people in that row, and there's 600 total students. So I'm thinking that's going to be 480 over 600, which is about, well, actually it is equal to 80%, 0.80 probability. Now look at part B and C, and I'm going to kind of go ahead and give it away. Is notice we're still looking at yes, taco tongue. Both of those say probably yes, taco tongue, probably yes, taco tongue. However, the difference is if you look at it, it says that given that, yes, evil eyebrow, given that, no evil eyebrow. So is the ability, part A, for someone to taco tongue, is it impacted by their ability to either be able to evil eyebrow or not evil eyebrow as it says there? So let's find out. And so if we're looking at this, we have probability of yes, taco tongue, given that yes, evil eyebrow. So really I'm going to focus starting right here. Yes, evil eyebrow, given that this occurred. That's a total of 200 students. So I'm looking here, there's 200 students, 180 have the ability to evil eyebrow. And so, and taco tongue, so therefore, I'm going to have 180 over 200, which that as a decimal is 0.90. So right away I can see something. Their ability to evil eyebrow impacted their ability to be able to yes, taco tongue. Their probability was impacted in this case. Better word than ability. Their probability was changed. Yes, taco tongue was 0.80, but as soon as I put a condition in play of yes, evil eyebrow, it changed the ability, the probability of them to be able to taco tongue. Let's see if it's the same for part C. Part C says yes, taco tongue, no evil eyebrow. Sorry, given that, no evil eyebrow. So given that, no evil eyebrow. And so we're focusing right here. Given that this occurred, that looks like there's 400 total people there. what is the probability that they can talk or tongue? Well, that's 300 out of that 400. So I'm thinking it's going to be 0.75. And so we're looking at that 75%. So notice someone's ability to yes, talk or tongue, just yes, talk or tongue, was 90%. But as soon as a condition was put into play on that of, given that they can yes, evil eyebrow, can they yes, talk or tongue, change the probability? Now it was 0.90. Also, if I said, hey, no evil eyebrow, given that condition, they cannot evil eyebrow, what's probably they can yes, talk or tongue? It changed that probability again, 0.75. So are these two events independent of each other? And the answer is going to be no. The probability of yes, talk or tongue is not the same probability of yes, talk or tongue, given that they can evil eyebrow, yes, evil eyebrow, which is even not the probability of yes, talk or tongue, given no evil eyebrow. So the probability changed, and it just has to change between two of them for it to be not independent. I wanted to show how all three are not equal. If they all three were equal, then we have probability independence. But given that something occurred, given that this occurred or this occurred, it changed that original probability, which means they are not independent of each other. So the question is, what would a two-way table look like if they were independent of each other? And that's where question 5 comes in. Suppose that the ability to talk or tongue and evil eyebrow are actually independent events. So let's just suppose they are. Pretend. Determine the following probabilities. Probability of yes, talk or tongue. Probability of yes, talk or tongue given yes, they can evil eyebrow. Probability of yes, talk or tongue given that no, they cannot evil eyebrow. And so in that case, I want to keep a couple things in mind. I want to keep in mind that if they are independent, this is what it means. The probability of the event is going to be the same as if the event occurs given that another event occurred or even its complement occurred. We've been looking at both of those. Yes, evil eyebrow, no evil eyebrow. So those two are complements of each other. So if they're independent, all three of those, or two of those, three out of them, like they all have to be the same. And so in that case, I need to check those conditions. And when we look at them, that's really what I have laid out in part A, part B, part C. Is if I'm focusing on this, part A is really the probability of event A. Yes, they can talk or tongue. Notice all of those are part A. Yes, they can talk or tongue. Yes, they can talk or tongue here. Yes, they can talk or tongue. Those are all your events. You want to determine independence, probability independence. Now, does another event occurring change part A? And that's what this is saying. Hey, given that they can evil eyebrow, is that going to change that probability of talk or tongue? Given that they cannot evil eyebrow, which is the complement of part B, does that change the probability of yes, they can talk or tongue? And so really that's what that symbol in the symbolic form up here is really trying to tell us is our A, our B, and our C here have to really be equal to each other if they are independent. So what I'm going to do is I'm going to figure out what they're going to be. And so first off, we already knew that this was 0.80. If the probability of someone to talk or tongue, just from our table that we had looked at before, was 80% for the so 0.80. If they are independent of each other, all three of those have to be the same value. That's really what that formula is saying and what it means in words. The probability does not change given that something occurred. And so that's where part B and part C come into play. So we're going to look at that and actually find out what should a two-way table look like if they are independent of each other. And that's where questions 6 and 7 come into play. Fill in the table based off of these probabilities. So the probability for all of those has to be 80%, 0.80. So the probability that we know given to us, 480 out of the 600, was yes, talk or tongue. That's 80%. So that one's set. That one's good. That's the probability of event A. Now if I want this, the probability of yes, evil eyebrow, given that yes, evil eyebrow, yes, talk or tongue, that needs to be 80% of the 200. Because remember, what we had before is when we look at original probability and go back to the original problem, we had this cell divided by 200. And so I need to find out what is 80% of that 200. And it also goes for the other column that we're dealing with. The other column says, hey, we said given that no, they cannot evil eyebrow, what's probably yes, talk or tongue? And we had our number over 400. And so we had this over 400. That's where we got that 0.75 before. But now we're saying we want independence, so it has to be 80%. So what I'm going to do is I am going to fill them in with 80%. 80% of 200 is 160. 80% of 400 is 320. And then I know this column has to add up to 200, so that's where I got the 40. And this column needs to add up to 400, and that's where I got the 80. So notice how it relates. Is this divided by this, this divided by this, this divided by this, all has to be the same probability in order for them to be independent. And so we could see a nice little visual of, if I'm focusing on my information, these divided by 160 divided by 200, 320 divided by 400, 40 divided by 600, they all have to be equal to each other. So if you ever want to know if two events are independent of each other, you need to check the conditional probability and relate it to just the original. And so we had the original, and the original was 480 divided by 600. The ability for somebody to talk with tongue was 80%. I need to check the conditional probabilities and to see, are they equivalent? So I need to see, is 160 divided by 200 also 80%? Is 320 divided by 400 also 80%? And that's really what this is checking. And so this is for a way for us to check if two events are independent of each other. So now we're going to focus on those quick concepts, those quick notes of conditional independent probability. And I'm just going to pull up the information for us and kind of talk through it. Conditional probability, that's the meat. That helps us determine if two events are independent of each other. So conditional probability is the probability of one event given that. That's the new phrasing you're going to hear, and that also has the symbolic form we can see right here of what given that looks like. So given that, that's a vertical line, event B occurred, what's the probability of event A happening? Now the mathematical formula for that is the probability of A and B. So the probability of A and B, that's intersection. And so remember, go back and think about it, we always dealt with the intersection in the two-way table there. So that's the probability of both happening. You can see I have it in words, and in red I have it in symbolic notation form. And the condition one is the one that goes on the bottom, which isn't too bad. You see, given that B, and that's kind of set up of given that probability of event B. And so you could tell, even in this form, kind of like a fraction, maybe you could think of what event goes on the bottom. Now, independent in words, knowing whether or not one event occurs does not change the probability of the other event. And what this means is the probability of event A is not going to change given that other events occurred. Those should all be equal to each other, and if that's true, then they're independent. And so that's really where independence comes in, which is what I really like what we did with the two-way table on the previous part of the notes of, I'm going to find my original probability, and I'm going to then check the conditionals, which really is kind of taking the rows and dividing by the totals below it, and they all need to be equal to each other in order for it to work. So visually, it's not too bad in this way. So the probability of an event happening will not change given that another event already occurred. And this is what that form means for us. So let's move on to the next part. And the next part is more mutually exclusive versus independent. Mutually exclusive, how do those relate to each other? I'm glad you asked. They are not the same. And this is a really hard thing for people to understand. Mutually exclusive does not mean independence. And I feel like our worldly definition of independent makes us think mutually exclusive is the same thing. And they're not. And I want to show it to you. Mutually exclusive means there is no intersection between two events. They have nothing in common. So if two events are mutually exclusive, the probability of event A given that event B would be the probability of A and B over the probability of B. I mean, that's the formula, right? The probability of event A given event B happens is their intersection divided by the probability of event B. Do you notice right here? Where do they intersect? And we said they don't intersect. We said that the probability of A intersect B, A and B is 0. And so we're looking at this. We can do some math to go through and help us figure out some of the notation for it. But really, I'm going to go right down to this. So what can we conclude? For mutually exclusive, the intersection, probability of A and B, is going to be equal to 0. They have no overlap. They have no events in common. For independent events, the probability of A and B, their intersection, cannot equal 0. Go back to our table from before when we had that 80%, 80%, 80%, is notice we had to have information in those cells to get that 80%. So for independent events, they have to have an intersection. For mutually exclusives, they don't. So one thing to kind of be aware is if two events are mutually exclusive, they cannot be independent events because the one event occurring impacted the other. And I want to show it to you, and I'll show it to you symbolic. I'll do a Venn diagram to help you with this. And then we'll look at it with a, let's say, cards problem. Is if we look at this, given that this event occurred, okay, so I'm only focusing on this part of my Venn diagram. I'm only focusing on event B. So given that this occurred, what's the probability if I'm only focusing on that circle? So you notice I got rid of the rest of the other circle. What's the probability of event A happening? Well, given that event B happened, I'm only looking at that circle. There is no A in there. There's no overlapping. A cannot happen if event B happens. So if event B happens, if this is my only place I'm looking at, there is no event A there. So the probability would be 0. And so the idea is mutually exclusive does not mean independence. They are not the same. And we could look at that perhaps with cards. The probability of, from a deck of cards, drawing a heart and a spade is 0. In other words, they're mutually exclusive. If I have a deck of cards and I randomly select one, the probability of that card being both a heart and a spade is impossible. Now, if hearts and spades are independent, the probability of drawing a heart, given that I already drew a spade, should be equal to each other. But I know the probability of drawing a heart, given that I drew a spade, has to be 0. But the probability of drawing a heart is 13 out of 52. So if two events are mutually exclusive, they cannot be independent. And it was a really big thing. It's one of the released questions from the 2002 AP exam. It says, which of the following statements is true for two events? If events are mutually exclusive, they are independent, and that is wrong. They do not mean the same thing. If they are independent, they must be mutually exclusive. And again, they don't mean the same thing. If the events are not mutually exclusive, they must be independent. That's interesting. If the events are not independent, they must be mutually exclusive. If events are mutually exclusive, they cannot be independent. And so in that case, if you have two events that are mutually exclusive, the probability of A given B, we're looking at, it has to be the same as the probability of event A happening and so on. Well, if they're mutually exclusive, A intersect B is 0. So then that would become a 0. And so therefore, if two events are mutually exclusive, they cannot be independent. It's like that was written on the previous slide. Odd. All right, so let's take a look. Some other things, and this from a website, mrdirksen.com, top 10 HTML. It says if two events are independent, the outcome of one will not affect the outcome of the other. Whether or not it rains or whether or not a coin flips head or tails don't impact each other. If two events are mutually exclusive, if one happens, the other event cannot happen. If I'm picking one M&M from a bag, I can find the probability of drawing green or red. But if I draw a green M&M, there's no way I can draw a red M&M because it's green. And so we can see from that previous one how mutually exclusive impacts independence. And you can see here are the formulas down here to kind of help you understand it a little bit more is your probability has to remain the same. This has to remain the same as this does in order for them to be independent of each other. So one last example to get us through. The Pew Research Center randomly selected 100 mothers in 1976, 1994, and 2014 and asked them how many children they have. This two-way table right there represents the information. Suppose we randomly select one of the survey respondents and we're defining, so we have some symbols here. C is the event of 4 or more children, S is the year 1976, N is the year 1994, and F is the year 2014. And so we're looking at this, I want to find the probability of C given S, and then interpret this in context. Ooh, I'll interpret. So we have a nice little stem there to help us with interpreting. So the probability of C given S is their intersection. So really, again, I'm just going to kind of focus on the main idea. So S is the year 1976. And so given that this occurred, so given that we're focusing on this column, 1976, what's the probability of 4 or more children? So I'm looking at the probability of 4 or more children in that row. Well, where do they intersect? Well, they intersect right here at 40, and that's really what this is asking us. Where does event C and event S occur at the same time? And they occur at 40. Out of, how many was there total in 1976? There was a total of 100. And that would be about, well, that is actually 0.4, 0.40, if that makes you feel better. So interpreting it, given that, well, given that what? What had to occur first? Well, the first thing was that the mother surveyed had to be surveyed in 1976. There is a 0.4 probability. If you have the notes, I did erase. You can cross out. There was a percent symbol right here. Get rid of that because I'm telling you probability, which is between 0 and 1. So given that the mother was surveyed in 1976, there was a 0.4 probability that she had 4 or more children. So there is interpreting our information based off of this two-way table. Same information for number 2, given that the chosen mother was not surveyed in 1976. So that's interesting. So I can see right here, given that the chosen mother was not surveyed in 1976. That's telling me complement. What is probability that she has 4 or more children? So in this case, write the probability as a statement using correct symbols. And so we have right here, given that event C happened, given that the mother chosen was not surveyed in 1976, so that's as complement. What's probably that of her having 4 or more children? So let's take a look at that. Probability of S complement would be, well, you're going to have to be in the other columns. I'm going to have to be over in this area. Given that this occurred, which means in this case, I have a total of 200 people who were not surveyed in 1976. How many of them have 4 or more children? And in that case, I would say it's about 26 of them, 13 and 13. So that would be a 13 out of 100, a 0.13 probability. All right, so what was our last one? Our last one was 40 over 100, 0.40 probability. This one is a 0.13 probability. I wonder if we're trying to build into something. Because notice the first one, I'm just going to write down here, was probability of C given S. Well, they're not equal to each other. I wonder if they're independent then. So if I look at this, they are not independent. And I threw a bonus one in here is kind of looking at that one. I'll talk about that at the end. So we can see that those two probabilities we found, 0.40 and 0.13, are not the same. So no, mothers in 1976, let's see, which one are they? So mothers in 1976, 0.40 is more than 0.13, are more likely to have 4 plus children than mothers not surveyed in 1976. So what does that mean? That means they're not equal to each other, so they are not independent of each other. By the way, it's not even equal to the original event occurring. The probability of having 4 or more children, and that's where this one comes into play, is 66. 4 or more children would be 66 out of 300. So let me kind of show you the visual again that we looked at before with the tables. If I look at the main idea, 4 or more children, this right here, I'm taking my information, this intersection, divided by the 100. I took this intersection, in this case it's not quite a two-way table because we have 3 columns, but the idea of the 26 I divided by the 200, and if I take the 66 and divide by the 300, are those probabilities the same? And in this case, they're not, so they're not independent of each other. So this is probability independence. It's a meaty topic. Luckily we'll have some practice the more we go in with probability over the next week. So I hope this kind of helped us with some ideas of given that conditional probabilities and its relationship with probability independence.